Okay, we'll start the lesson now. Do you hear me?
Yes.
Thanks. So double check your attendance before we start. Now, all right. So last time we talked about the variation of the melting point of period 2 and period 3 elements. So you may find some of the keywords in the paragraph, right? In the paragraph length answer, you need to go back to bonding and structure of those different particles. So remember, mention what are the particles involved, what are the electrostatic force between them, and most importantly, how do all those factors just we have mentioned affect the strength of those electrostatic force. So while this has a difference, and this will also affect the the strength of bonding will also affect our physical property. So this is our flow. With a recap of what you have learned. So here comes two more on the getting to know the periodic variation in the electrical conductivity. Take a look, electrical conductivity of period 2 and period 3 elements. So most of the time, you see it as metal. Now, please circle all those as metal. Just highlight that 3, they are metal. While we have got one where it is a semi-metal here, small. I try to use different color highlighted now. These two, boron and silicon, being semi-metal. So mark it is metal, metal. The blue one here. So it's semi-metal. And also this one's semi-metal. So for the remaining, they are non-metal. Okay, we start from this. So the conductivity of a substance will relate to any mobile charge particles, right? Mobile charge particles. In this sense, that mobile charge particles, we mention it as the localized electrons. Now, okay, but not mobile ions. The non-mobile ions are for these cases, all these elements in the periodic table. Okay, so and you may find the two circled one, lithium and beryllium. They are good electrical conductor because it is a metal, right? So due to the presence of the localized electrons, it is highly conductive. Okay, but boron, semi-metal, rather low, but not zero. So you may find a very slight difference between this one and other non-metals, just like nitrogen, oxygen, fluorine, etc. Carbon is a very special case. Take a look. Carbon is a very special case in form of graphite. And this will have the localized electrons that will travel along the graphene layer, but not between graphene layers. Just remember that term, along the graphene layers. So this is what I would like to share with you on that. How about period 3? Period 3, we focus on sodium, magnesium, and aluminum. When you compare this one with other non-metals and semi-metals, they are a relatively good electrical conductor because of the presence of, again, delocalized electrons. Okay, delocalized electrons. So our focus is on the variation from sodium to magnesium to aluminium. Okay, so it is explained by the number of the localized electrons per each atom law donates. Okay, so it depends on that. So this is the keywords I would like to mention. If you want to tell quantitatively, so the point to compare is from the term per metal atom. Okay, how many delocalized electrons can it be formed? So remember, this is a very important concept, but mainly talking about more or less will be problematic. So this is what I would like to remind all of you. Sorry to say that my computer is running out of battery, so I'll need to move the setup a little bit such that I can see you here, right? Good. Now, so this is the one, and when compared with sodium, magnesium, and aluminium, right? We have got the trend. We have got the increasing trend. Okay, we've got the increasing trend. So you may got each sodium atom to donate 1 electron, outermost shell electrons for delocalization. Magnesium is 2, aluminium is 3. Can you see that? So there will be more delocalized electrons available to drift through the structure when experience and electric field, under electric field. So aluminium, the conductivity of it is much better when you compare with sodium and magnesium. Okay, number 1 is aluminium, number 2 is magnesium, number 3 is sodium. When you compare this with other substances such as silicon was said to be a semi-metal or metalloid because of the structure, giant covalent structure. Theoretically, you may find that there will be no delocalized electrons in this structure because all electrons in the outermost shells, they're involved in the bonding, in the covalent bond between among those neighboring atoms. But at room temperature, you may experience some few electrons that will gain enough energy to become delocalized. And this effect will be more obvious while we are having at high temperature. Okay, so you may find more electrons that will gain enough energy to become delocalized. So for silicon, you want to talk about its conductivity. It varies upon different temperatures. For low temperature, it's low, but for high temperature, the conductivity will become higher because of the more energy gained from each electrons that become delocalized. Do you understand? However, while you talk about non-metal, all those they neither have mobile electrons, delocalized nor mobile ions. As a result, we will tell those non-metals and non-conductor. Okay, no mobile ions, no delocalized electrons. Now, just a factual recall of what you know it last time. Class practice 41.2. Now, please do it together. Recall your memory about bonding and structure. What is that? Wang Junhei. Wang Junhei. Wang Junhei. Yes. Tell me your understanding about that. Yes, sodium, metallic bond. Yeah. What else? the salt as magnesium. So the structure is giant metallic structure. So what else for silicon? Being covalent, covalent bond between atoms. So it will have an extended network. The structure, it is giant covalent structure. How about phosphorus? What are the bondings involved? What are the bondings involved? So it is still covalent bonding between atoms. But if you want to talk about between molecules, this is 12 force. So P would exist in a molecule. P4. Do you still remember? P4. So this is a molecule having 4 atoms. They will covalently connected to each other. Still remember the structure? Still remember structure? What is that? It will be a tetrahedrally shaped substance, P. While each P, remember to connect it by 3 covalent bonds with the neighboring phosphorus atom. So please check this line. This one, it is just the bonding behind the PP bond at front. Okay, so it's not a cross. It's not a cross. Instead, it is just a hidden line, much far behind the plane. Can you get my point? So to form a tetrahedral structure, B. Now this is what you may know it in essay type question. How will you arrange sodium, magnesium, silicon, and phosphorus in order of decreasing electrical conductivity at room conditions? And afterwards, you are going to explain in terms of their structure. How will you answer? The answer you may find in previous pages, okay? But I need your contribution. Tell me what will it be written like? Let me check this one. I need to plug. I need to plug in with the power supply. Oh God. I'll give you some time to finish this. And I would like to check your understanding, your paragraph link answer shortly. First of all, the trend. What is the trend? Tell me your trend. Trend. What is the order? Oh, 就進the order. Decreasing order.
Magnesium 先，跟住再到 sodium，跟住silicon，最後 phosphorus。
Yeah. Oh, reasons. So in order to answer that reasons, you may need to tell the difference in bonding and structure separately, and then do it as a start to compare. Okay. First of all, how you will get a peripheral sodium? Altogether, we have got it in 3 groups. Magnesium and sodium, they are in a group. They both have giant metallic structure. Okay. With metal ions are bonded by the localized electrons by metallic bond. So we focus on the metallic bond, the delocalized electrons. So they have high electrical conductivity because of the presence of delocalized electrons. All right, so so this is the sentence for you to compare. Okay, what to compare is about the others. So if you want to talk about silicon, so what is that? Silicon, they will have a giant covalent structure inside with atoms are strongly bonded by covalent bond. But at room temperature, very few electrons are said to be delocalized, right? Why? They will gain enough energy. So it conducts electricity. Of course, you may say that at higher temperature, what will happen? They will have more electrons, they will gain enough energy and become delocalized. So it will give rises to the conductivity of silicon. So we'll call that. So silicon is therefore said to be a semi-metal or semiconductor because you focus on semiconductor. Okay. How about the last one? phosphorus. Phosphorus has a simple molecular structure. Now remember the form, it is in form of P4 with molecules held together by weak van der Waals forces. It cannot conduct electricity as it does not contain any mobile ions nor delocalized electrons. Now, but once you type all those like here, you focus on the comparison between those substances of three groups, okay? But you would miss out the point about the conductivity of magnesium and sodium. Okay, so lastly, you are going to write here, tell me the difference between the conductivity of sodium, magnesium and sodium. Okay, magnesium and sodium. So how does it how is it related to梁家傑? Oh, I see Chen海have marked something. Try to take a look on what his work. Every sodium atoms donate one electrons, outermost shell electrons, to become localized electrons, while magnesium atom donates 2. So the number of the localized magnesium is higher than sodium. Yes, that's right. You can say so. Merely you may find such. Yes, that's right. What else? How about you, Yuan Ge? Is it okay? Yuan Ge. Typing. Okay, wait for you. Okay, any questions for so far for this? So when you would type this, okay? So when will you type this red one? Okay, so red one, it is just a the following up of these two. You are going to compare, right? A further elaboration of comparing the difference in conductivity between magnesium and sodium. But the green words should come first because it is the starting point for you to group the 4 elements into 3 groups. So each of the group would have their own characteristics. So we start from this. So which means that if you write down the green one only, you would have the following conclusion, right? So metal as a group, semi-metal as a group, and phosphorus as a group. And later on, the writing of red words follow because it will supplement the further comparison between magnesium and sodium in terms of electrical conductivity. Do you understand? So it really agrees with our thinking that whenever you're going to do the comparison, try to make a rough comparison first of all. The rough comparison would come from comparing the elements with totally different structure and totally different bonding. We start from this. While you do the grouping, you may experience some more further comparison. So for those some more comparison, just like magnesium and sodium, you are going to compare on the same graph per atom. Okay, how many atoms will be donated to form the localized electrons? Do you understand? So do you find the scope? Do you find the scope? From big to small, right? Full sodium, magnesium, the delocalized electrons. Okay, so you mentioned, like you just submitted your work. You mentioned both metals, they have giant metal structure. But the second sentence, the delocalized electrons are closer to the nucleus in magnesium. This is correct. It's correct, but it doesn't help too much in relating to higher electrical conductivity in magnesium when you compare with sodium. If you want to compare quantitatively the conductivity in between metals, you are mentioning how many delocalized electrons does it have per atom that may come from the loss of electrons from a metal atom for each metal atom. So you go back to group. So the quantitative way to express is not the term closer or nearer, closer or further apart from the nucleus. What I mean is delocalized electrons and the nucleus, but the number. Remember, but the number. Do you understand? It's not distance that matters, but the number. Questions? Do you understand? How about the others? Do you understand the whole flow? Now you may let me know your understanding, right, in your chat box or in your name next to it. Check or cross, tell me. You understand or not understand? 唔關嗰個距離事啊 ，delocalized electrons 係咪距離個 nucleus 近或遠？嗰個咧就係講咩咧？好多時幾時會用呢招咧？就係講緊例如話atom 嘅嗰粒 atom 嘅 size 係咪 ？size of atom。We usually measure it as atomic radius. So this is our definition, right? From the reference point to the furthest point. While the furthest point is exactly the outermost shell. Okay. But for conductivity, you are talking about how much charge can transfer in certain period of time, right? You talk about current, the concept of current, right? So go back to number of delocalized electrons in different environment. Well, it comes from the donation of electrons from each metal atom. Understood? Understood. Okay. Shall we continue? Now, there will be more to come. Now, for example, atomic radius, electronegativity, density. So you may find the later part, find and share. Can you see that? Find and share. So please please take a look on this. On here. Do you know the trend? Atomic radius, electrical conductivity, and density. Do you know the trend? Do you know the trend? Do you need to know it now? Please search it on the web. Now, whenever you talk about periodic pattern and come up with these terms, you check the Google photo, Google pictures, and you will usually see some trends in pictorial representation. It will give you have an easier life, right? Tell me. What are the trends? First of all, atomic radius. You know what is the trend in the difference in atomic radius across the group? Across the group, Lei Cheng, do you know?
Decreases in size.
Yep, decreases in size. So you may, but of course, the trend, the way to answer will become a little bit different. So you may take along the word on here. It is because you want to talk about the atomic size. We have got different definition. So we have got metallic radius, covalent radius, atomic radius. So many different definition in university study. But don't worry too much about that point. We focus on the across the period first of all. Across the period, the size decreases, and it is because of what? Effective. It's because of what? Effective nuclear charge. Do you still remember that? Effective nuclear charge. So the further addition of proton and electrons to each atom across the period will increase both the electrostatic attraction between the nuclear attraction, or between the nucleus and the outermost shell electrons, and shielding effect, which is defined as an electron repulsion. Do you still remember the two terms? However, the increase in nuclear charge, right, will be more dominant. Okay, the extent of increase of that will be one higher. So you would say that experiencing effectively larger effective nuclear charge, which means that those outermost shell electrons they are pulled more strongly, okay, across the period towards the nucleus of atom. So they will give you a decreasing trend. Now, how about down the group? Down the group, why would have got atomic radius increase down the group?
More occupied electron shells.
Yes, more occupied electron shells. So the shielding is more obvious. So remember, we have got the primary shielding, the shielding between the inner shells, the electrons in inner shells and outer shells. That type of screening, that type of electron repulsion is more significant. So the outermost shells is said to be further away from the nucleus when you compare with this with the other elements in the same group. Okay, can you get my point? So the atomic radius will increase down the group, but it decrease across the period.
正常嘅問題啦。
Yes.
咁可唔可以重複一次？點解佢會細咗？我即係我啱啱即係我聽到佢話 shielding effect 大咗，但係有啲嘢 significant 過佢啦。咁係咩嚟？
The nuclear charge or what we call it as a nuclear attraction. What is mean by nuclear attraction? Nuclear attraction is defined now. So atomic radius, first of all, how to define the atomic radius is from the distance between nucleus and the outermost shell. So whenever you talk about this one, you need to tackle the relative position of outermost shell electrons. But the outermost shell electrons with a relative position based on 2 points. One is the nucleus, how many positive charge would attract those outermost shell electrons. We will call that nuclear attraction. The other one is electron repulsion, or we call it shielding, or we call that screening. So nuclear attraction is somewhat a positive and negative, but for this we mainly focus on negative. Across a period, what will happen? Number of protons increase and number of electrons will increase, right? So this will make these two factors going to different extremes, okay? Two extremes. But the extent of increase in nuclear attraction outweighs the increase in electron repulsion. Okay, you get my point. So we will say that overall, we have got a net stronger nuclear attraction. So we will collectively call it as a nuclear charge, or we call it effective nuclear charge. So, which will say that the outermost shell electrons, they are being pulled closer to the nucleus. So as a result, we will say that there will be decreasing trend in atomic radius across a period. Okay, now so this is what we talk about in this direction. How about down the group is another case because of our more occupied electron shells, right? While the shielding is more dominant, okay, because of we still have electrons in inner shell. So the inner shell, they will have a more significant shielding in between. Okay, this one is stronger. Stronger what? Stronger repulsion, but not attraction. While you compare with this electrons and this electrons, we could also got a repulsion, but it's relatively weaker. Do you understand? So even though I increase the number of electrons, that type of shielding is will contribute less to a less extent when you compare with this and nuclear attraction. So we call that effective nuclear charge. OK， 明唔明？咁打橫睇打棟睇唔一樣嘅，得唔得？ So what we say that overall, you may say that you experience a increase, but the increase it is roughly, you may see from the book, they will say that shielding is, the increase in shielding is not so obvious. Somebody may also argue that that type of shielding is just more or less the same when you compare group 1 to the group on the right hand side. 有啲人咁講嘅。But to me, if you want to really know that adding the outermost shell electrons into the same outermost shell, they will also contribute larger shielding. But that so-called larger is not so significant. 明唔明? So we call it effective nuclear charge. So, but it's more obvious when you add one more proton and one more electrons, we to experience a stronger nuclear attraction. The attraction between nucleus and the outermost shell. Understood? Ming? Now you may find the others by yourself. I don't want to mention one by one. Now, how about electrical conductivity? What is a trend? 我淨係講個 trend 啫，解釋嘅。You leave it by yourself. the trend will be increased, right? Increase across the period. How about down the group? It will decrease, okay? All of you, please mark it down. Increase across a period, but decrease down a group. But for density, the trend would agree mainly with the packing, while the packing of those particles is much related to what? It's much related to what? Bonding and structure. Recall your memory about density. The definition of density is to find out per unit volume what is the mass of the substance. So it is something related to packing. But you know that the packing, it also depends on the bonding and structure of those elements. 咁應該你識㗎啦，呢啲我唔講啦，你自己上網揾到㗎啦。Questions? Now, if not, we would come to the peripheral elements about the chemical property. Chemical. 頭先講咗係 physical 嘛。How about chemical property? Of course, there are quite a lot of coverage about this, about the chemical property. But in DSC syllabus, on the formation of oxide. So for the following equations, you may see all those they will talk about the formation of oxide. Namely this one, first of all, potassium oxide. For or sodium oxide, sodium group 1 will also has a chance of having peroxide with the formula O2. What is that? 2 minus. Do you still remember that one? This is what we call it as a peroxide. So you may find some superoxide as well. Superoxide. So we have got the formula of O2 minus. While this, you may find it in potassium downward. But for peroxide, you may find it from sodium downward. So which means that for potassium, it will have a chance of having potassium superoxide, while not in potassium peroxide. Now, why is it like that? Because how about group 2? Group 2, it will be quite rare to find peroxide. Why? It's because of the stability of these peroxide and superoxide when you compare with normal oxide. Peroxide and superoxide is relatively less stable, so the electrons will become more diffuse. Now, for example, this peroxide, while the superoxide will have this structure. So those electrons, this is because of the difference in charge. So it will make you more diffuse when you compare with normal oxide. Now this two group, okay? But if you want to talk about the approaching of the sodium potassium ion nearby, it may experience a distortion of electron cloud to make these peroxide or superoxide back to normal oxide. Now this it will easily happen if I apply heat. Okay, so how would you distort the electron cloud besides heating? I may think of the charge, right? If you have a chance of having a positive ion, the cation of high charge, you may tend to distort the electron cloud of oxide. Now, no need to mention it is peroxide or superoxide. Now, because as I said before, the electron cloud of peroxide and superoxide ion, they are more diffuse. So if I have got a metal ion of higher charge, it would have a more easily distorted peroxide or superoxide structure, even at room temperature. In other words, the formation of peroxide or superoxide are rarely found when you talk about group 2 or group 3 elements. Is that clear? Because those two metal ions, they are of higher charge. It will distort the electron cloud of these, okay, or this more easily. Do you understand? And do you mean that, Mr. Jim, if the anion is of a bigger molecule, right, would they have a chance of undergoing decomposition upon heating? Yes. So it is quite commonly found to see nitrate ion and carbonate ion, for example. So upon heating, so they will decompose, right? So the reason behind would be something like this, because of the distortion of electron cloud of those ions when you have a cation next to it. Okay, if you don't understand that, don't worry. Just memorize the occurrence for peroxide found in group 1 usually. But for magnesium, aluminium, low such chance. If you don't understand that, don't worry. Just memorize of that first of all. But for silicon, the oxide is SiO2. Now this one you may find it quite hard to memorize. Phosphorus P4O10, sulfur SO2 or SO3, chlorine, various oxide with different oxidation number. Please check the oxidation number. The first one is +1. Second one is plus what?
+4.
And then now you may count it by yourself, okay? So you may find chlorine, they would have a variable oxidation states. Now, because of what? Because it can have a extension of octet. Why? They've got an available shell for accommodating more electrons to form a bond. Okay? Questions? Now, the further comparison will lies on the property of the oxide of peripheral elements. And so DSC exam, they will be asked every 4 to 5 years, okay? So we'll tell it in repeatedly. So you go back to the bond structure. This time, please separate into different parts. This, and this. 3 different groups. One is ionic oxide. So you may find it here. While the other two, we call that a covalent oxide. But we will want to have a further split of covalent oxide. You may have this one being a giant structure, while for phosphorus oxide, sulfur oxide, and chlorine oxide, it only contains simple molecular structure. But for ionic oxide, most of them or all of them, we talk it as a giant ionic structure. All of you, please mark it down. Giant ionic structure. For SiO2, giant covalent. Finally, for other non-metal oxide, they will process simple molecular structure. Questions? Now, if you want to take a look at the composition of period 3 oxide, you may get something else. So first of all, the melting point. Now, for giant structure, do you see that? What can you relate them? Giant structure, relatively higher melting point. Simple structure, relatively lower. You know it, okay? Second, conductivity. Conductivity, what else? When molten, these three will have a good electrical conductivity, but none can be found for the other oxide. Why? 大家仲記唔記得點答啊呢個 ？Because of what? At high temperature, when molten, the ions will become mobile. All of you mark it down. Ions become mobile. So it is easy seen that for the giant metal ionic structure, and when molten, those substances will have conductivity. Okay. 3, the composition of the oxide appear 3 elements. So you may find the trend from Na2O to Cl2O7. What can it be concluded is the number, on average, number of atoms, oxygen atoms combining with 1 mole of atoms. It will have a higher trend. Can you see that? Higher trend. So which means that for sodium, per sodium atom to form the oxide, it would have 0.5 oxygen atoms connected to that. But for chlorine, it will be risen to the maximum of 3.5. Can you see that? Now, please count this, right? And you can get what I mean. The number of oxygen over the other atoms to be considered. So you may get the number. And for lastly, it's about the reactions. The reaction between the peripheral oxides with water. So please memorize those equations. So you may find sodium oxide dissolve water to form hydroxide, so alkaline. Okay, magnesium oxide they would react with hot water to become slightly alkaline solution. That only happens in hot water or boiling water. So we would call sodium oxide and magnesium oxide and alkaline oxide or basic oxide. All of you, please mark it down. Now, the term basic is different from what you know in English. So the basic means the chemical, it forms part of the salt making process. So we call it basic oxide. Especially while we're talking about as alkaline oxide, which means that it can dissolve in water to form an alkaline solution. alkaline solution. How about aluminum oxide? Now, aluminum oxide is very strange example. Now, it is water insoluble. It will not be able to form alkaline solution. Yes, unfortunately, it will say yes. But does it mean that it is not a basic oxide nor alkaline oxide acid? No. It's also basic, it's also acid.
錢 Sir，錢 Sir，
Yes.
你係咪冚住個咪有啲好朦？
係邊度聽到？
有啲朦。
呢度。How about
而
this？
家 OK，啱把聲有啲朦啊。
啱邊句啊？我由邊句開始講翻？
而家 OK。
講到 aluminium oxide 有咩特別嗰
Aluminum oxide, it is also called it as a basic oxide, but not say it as an alkaline oxide because first of all, it does not dissolve in water to form alkaline solution, but we will also call it as a basic oxide. So later on, you may get to know that it is also an acidic oxide. So you will know it later in the later pages. Very strange. It acts as a both acidic and basic oxide. How about silicon dioxide? Silicon dioxide is water insoluble, but we will say it will describe it as an acidic oxide. But do you mean that, Mr. Chin, silicon dioxide dissolve in water to form acidic solution? No, but instead it will behave chemically like an acid by reacting with what? A base. Or react with an alkaline. So I would like to talk to this later. Now, how about this? So also react with this and this. How about those other simple molecular structure? Merely put it into water, would it form an acid with various forms? So you may focus on the form on these right here. You may see, right? We have with water to form acid. All those hydrogen atom here, they are said to can be ionized. So, but the name of the acid is different, from ranging from methyl phosphorus, phosphoric acid, sulfurous acid, sulfuric acid, hypochlorous acid, etc. So in short, what is meant by that? If you want to talk about the oxide of period elements with water for sodium and magnesium, it may form an hydroxide solution with an alkaline solution. Besides aluminium and silicon oxide, in which it is water insoluble, we skip it. For phosphorus, sulfur, chlorine, whatever oxide form, they will also form an acid. So the water, the solution form would have a lower pH. So we call that an acidic oxide. But the question comes, how come we will say aluminum oxide and a basic oxide or acidic oxide and silicon oxide being an acidic oxide? So we come to the acid-base behavior. So what is mean by acid-base behavior? The action between this chemical with acid or alkaline. I put this as a first example, and you can get what I mean. For example, for sodium oxide or aluminum oxide or magnesium oxide, so they would all react with acid to form salts and water. So what is the type of reaction? We will call it as neutralization reaction. Okay, so if I say that it's an acid, how will you define this? It is a base, right? So that is the base, that oxide is a base, we call it basic oxide. Do you understand? That you do that similarly, irrespective of different forms of acid. HCl, H2SO4, react with that oxide, they will also react with salt and water. So for magnesium oxide, according to this definition, we can also say that it is the basic oxide. Do you understand? How about aluminum oxide? Aluminum oxide can react with acid. Okay, so to form salts and water. So if it is an acid, we call it is a base. So we will say aluminum oxide, a basic oxide. Can you get my point? However, if I have aluminum oxide, we add with alkaline, they will also form a salt. So it seems that if that is the case, salt, alkali for NaOH, this one, it is forced to define it as an acid. Can you get my point? So this Al2O3 act as an acid in this equation. So we will call aluminum oxide, they will behave both an acid and a base. So it depends on the partner. When it meets acid, Al2O3 would behave it as a base. Okay, now so the this one is an example. But on the other hand, you may find aluminum oxide reacts with alkali, it behaves as an acid. I put this as example and you can get what I mean. What is that? This one, we call that sodium. Do you still remember that chemical? Sodium aluminate. While aluminate, it is a complex ion, anion, with a formula Al bracket OH4 with an overall charge minus aluminate. Or you will use the word tetrahydroxyl aluminate. Now hydroxyl means OH minus, tetra means 4, aluminate means that it's a complex ion. So for aluminum oxide, it is said to be a very special case by naming it as a amphoteric oxide. Amphoteric, which means that they can have dual property. Amphoteric 得唔得？率兩性的 amphoteric. How about the other cases? I pick up silicon oxide, dioxide as example. When it reacts with an alkali, it seems like it can act as an acid by having sodium silicate. Just remember, silicate and water, salt and water is a product. So in this acid neutralization reaction, SiO2 behave it as an acid. Now, even despite the fact that SiO2 is not water soluble, but once we would come in contact with alkaline, SiO2 also react to form salt and water. So we call that SiO2 and acidic oxide. No need to mention some others. You may easily understood that for the other cases, all those it is said to be an acid. Well, because you have a base to form a salt and water. Okay. So what should be done? What should be done is to learn how to memorize those different equations while you're being asked. Now the overall pattern in ionic oxide, they are basic. Covalent oxide, they are acidic. Aluminum oxide is amphoteric. Across the period, the acid-base property will be from basic oxide on the left-hand side, amphoteric oxide in between, and acidic oxide on the right-hand side, with the corresponding formula, with the corresponding equations when it reacts with acid and alkaline respectively. Do you understand? Instead of just merely telling it is water soluble or not. 明唔明? If you want to further describe the acid-base property, never use an example of dissolving water because we have got a for yourself. You know what are the traps? They are the traps. They are not water soluble, but we would say SL2 being acidic oxide. The reason behind is it reacts with alkaline to form solid water. Do you understand? But for Al2O3, a very, very special case in which it can have dual property. It can behave as an acid when meets alkaline. It can as an alkaline when meeting acid. 有冇嘢問？有冇嘢問？ To mark the end of today's lesson, could you please have a quick check on 41.3? Do it together. The questions is about the elements in the period 3 from sodium to phosphorus and the oxides. Element X form an oxide with a low metal amount, a very key word. The oxide dissolved water to an acidic solution. What type of structure does it oxide of X have? Can you make a guess? What structure does it have? What elements should be near the left-hand side or right-hand side in the periodic table? Now, after you get to know the description here, tell me.
Yes.
Yes. From sodium to phosphorus, what can it be?
Would be
For oxide.
phosphorus.
Yes, phosphorus.
Yes. Okay.
And yes, please continue. Yeah, phosphorus is like phosphorus.
It's phosphorus. X should be phosphorus, and the oxide should have a simple molecular structure.
Now, simple molecular structure. So it will dissolve in water to form an acidic solution. So the equation, can you suggest the equations? Cyrus, what is the form of the oxide? P4O10 first of all.
Plus 6 H2O.
To form
and to form 4 moles of phosphoric acid.
4 H3PO4. Now, so remember, somebody may find it difficult to write down such equation. Please check the oxidation state of phosphorus. What is the oxidation state of phosphorus? It's +5. There is no change in the oxidation number of phosphorus. So whenever you are asked to write down the equations for the dissolution of oxide in water to form an acid, so please stick back to this rule. The oxidation number of phosphorus doesn't change. In other words, so as oxygen and hydrogen. In other words, this is not a redox. Remember, this equation is not a redox. B. Element Y reacts breakfastly with water, and also Y dissolved water to a solution of pH of 14, a very alkaline solution. What type of structure does the oxide Y have? What we expect to be Y? Which element is it? Now, some keywords. Reacts breakfastly with water. The oxide dissolved in water to form an alkaline solution. You have got quite 5 choices: sodium, magnesium, aluminium, silicon, and phosphorus. What can it be? Ammonia.
Sodium.
Sodium. Yep. Please continue. Sodium. So the structure is
A giant ionic structure. Oxide.
And then
Na2O solid，然之後加 H2O 就2個 NaOH。
Yep, Na2O, H2O to form NaOH with the mole ratio 1:1:2. Okay, two sodium hydroxide. Thank you. How about number 3? Element Z form amphoteric oxide, a very important term. Amphoteric oxide, the only choice. Only choice. What is it? The only choice.
Z is aluminium.
C is aluminium. So what type of structure does
Giant
aluminium
ionic
oxide?
structure.
Still giant ionic structure. Still giant ionic. But you write down the equation to show the amphoteric nature. What will you write?
First, we add the oxide of Z with H2SO4.
H2SO4. So it symbolizes aluminum oxide being basic, okay? To form salt and water. So what is the salt?
Aluminum sulfate.
Al2 bracket SO4 bracket 3 and H2O. So check mole ratio. 1313. Okay? 1313. How about the second equation?
We add the aluminum oxide with sodium hydroxide.
Yep, sodium hydroxide. So the salt form is, what is that?
Sodium aluminate.
Yeah, sodium aluminate. So with the formula NaAl bracket OH4 with a mole ratio 1, 2, 3, 2. Okay, only by showing this, you may say that it is a base for aluminum oxide on the first equation. For the second one, it will say it as an acidic oxide. We've got dual property, we call it amphoteric. State how the acid-base behavior of oxide of element can be used to identify whether the element is a metal or non-metal. Can you make such pattern? What type of oxide they are said to be basic and what type of oxide they are said to be acidic? Now to mark the conclusion of this part.
The ionic oxide are basic and the covalent oxide are acidic.
Of an element. So what is meant by ionic oxide?
A metal.
Yep, the metal oxide. They are said to be basic oxide. So now for non-metal oxide, it is an acidic oxide. Also, somebody may argue, metal oxide, is it an ionic oxide? Yes. Now the non-metal, it is a covalent oxide. Yes, that's right. So to mark the end of today's chapter, we talk about the electrical conductivity of the period 3 or period 2 elements. So this is what we have mentioned. The variation of electrical conductivity in terms of bonding structure mentioned. The period 3 elements reaction with oxygen water form oxide. The form, the bonding and stoichiometrical position, you know it. Variation of behavior of oxide with water, you know it. Be aware of the two cases. These two chemical is water insoluble, but you would want to mention several acid-base property, find their partners, find their counterparts. Okay, for example, if you think that that oxide is acidic oxide, which means that it reacts with a base. Okay, can you get a point? So you think that the oxide is a basic oxide, please think of a reaction with acid. So this marks the end of today's chapter. Any questions so far? So far, easy, difficult, or just memorizing something? Yes, to me, to both of you, it's just a memorizing of something. Let me know your understanding today. Any more questions? Okay. Now, so I would like to stop here, and today is Thursday, isn't it? Thursday. Thursday we have got an essay for 5B, 5A and 5B for tomorrow. I'll remember to submit your essay today. So you know the topic, right? Please check Google Drive and you may have it. Okay, so much for today. I'd like to see you in the next lesson. Bye-bye.
Bye, Caesar.
拜拜。
Bye-bye. Bye-bye.
Bye.
Bye. Bye. Bye, guys.